Hello, everyone. Tonight, we will embark on a journey into the mysterious depths of the nebulae. Nebulae are some of the most peaceful objects in the universe to think about because they look dramatic, but they behave slowly. They are not explosions frozen in place. They are wide, thin environments, gas, dust, and starlight changing shape over thousands to millions of years, like weather that never needs to hurry. Tonight, settle in and let your attention soften. You don't have to picture everything perfectly. Just follow the story in a slow, steady rhythm as we drift through what nebulas are, how they form, why they glow, and what they quietly do for the life cycle of galaxies. A nebula is, at its simplest, a cloud in space. The word comes from an old idea of mist or cloud, and historically it was used for many fuzzy-looking things in telescopes, including galaxies. But in modern astronomy, when we say nebula, we usually mean a region of interstellar matter, mostly gas and dust, spread out in a way that can be seen because it either emits light, reflects light, absorbs light, or bends light. Nebulas are not solid. They do not have hard edges. They are not like a mountain floating in space. Their boundaries are more like coastlines drawn in fog. You can trace a bright outline in a photograph, but the material continues beyond it, thinning gradually into the background. And most of the time, a nebula is incredibly diffuse. If you were inside one, you would not feel it like a thick cloud on Earth. The density is far lower than any vacuum chamber you could reasonably build at home. Yet, on the scale of light years, even that thin material becomes meaningful. It can block starlight. It can cool and collapse into new stars. It can glow with energy from nearby radiation. It can carry the chemical fingerprints of ancient stellar deaths. Nebulas are places where the galaxy shows its textures. They are also a reminder of something quietly beautiful. Space is not only empty distance between stars. Space is a medium. A thin one, but a real one threaded with magnetic fields, stirred by shock waves, seeded with dust, and enriched over billions of years by generations of stars. To understand nebulas, it helps to begin with what they are made of. Most nebular gas is hydrogen, because most of the universe is hydrogen. There is also helium and small amounts of heavier elements: carbon, nitrogen, oxygen, neon, sulfur, iron, and many others present as atoms, ions, and molecules. Small amounts sounds unimportant, but those heavier elements matter enormously. They help gas cool. They create bright emission lines. They form molecules. They build dust grains. They eventually become the ingredients of planets and, in at least one known case, life. Then there is dust. Interstellar dust grains are tiny, often comparable in size to smoke particles. They are made of silicate minerals, carbon-rich compounds, and in cold regions, icy coatings of water, carbon dioxide, methane, ammonia, and other simple molecules. Dust is a small fraction of the mass, but it has an oversized influence because it interacts strongly with light. Dust can absorb and scatter visible light, making dark lanes and shadowy shapes. It can also re-emit energy in the infrared, so a nebula that looks dark in optical images can glow warmly in infrared. This is why nebulas can feel like contradictions. They can be bright and dark at the same time, depending on how you look. And that leads naturally to the main types of nebulas, not as strict boxes, but as gentle categories, based on what makes them visible. Some nebulas glow because the gas itself is emitting light. These are emission nebulas. Some are visible because they reflect starlight, like cosmic dust acting as a soft mirror. These are reflection nebulas. Some are visible because they block light behind them, appearing as silhouettes and dark lanes. These are dark nebulas. And some are shaped by the end of a star's life, shells of gas cast off gently by sun-like stars, called planetary nebulas, or the more violent and energetic supernova remnants from massive stellar explosions. There are also nebulas that are mostly molecular and cold molecular clouds, often not bright in visible light, but rich in radio and infrared signatures. These are the deep nurseries where stars begin. But these categories blend into each other. A single region can contain bright emission, dusty reflection, and dense dark filaments all at once. Nature rarely labels its own work. So let's begin with the kind many people picture first: glowing emission nebulas, often pink or red in photographs, with dark pillars and bright edges. An emission nebula shines because its gas has been energized. Usually, the main source of energy is ultraviolet radiation from hot, young, massive stars, stars of spectral type O and B. These stars are extremely luminous and extremely hot. They produce large amounts of ultraviolet photons, energetic enough to ionize hydrogen, to strip electrons away from protons. When hydrogen is ionized, you have a plasma, free electrons and protons moving in the same region. Over time, those electrons can recombine with protons, falling back into bound states. And when they do, they emit photons at specific wavelengths. One of the most famous is the deep red hydrogen alpha line. That's a major reason many emission nebulas appear reddish. The nebula is not on fire. It is glowing through atomic processes, ionization, and recombination, plus emission from other elements like oxygen and sulfur that produce greenish and bluish lines in certain filters. In color images, especially those created with narrowband filters, the palette can be enhanced or mapped creatively to show structure. The colors are real in the sense that they correspond to real wavelengths, but the exact hues you see in famous images are often artistic choices designed to reveal detail and contrast. Even without focusing on color, the physics is quietly elegant. Light from a star enters a cloud. It changes the state of atoms. Those atoms then emit light. The nebula becomes visible not because it has its own independent energy source, but because it is being illuminated and energized by starlight, like a fog bank lit from within by a street lamp. Except the fog bank is light years across, and the lamp is a star that could outshine 1,000,000 suns. Where the radiation is strongest, the gas can become fully ionized, forming an H2 region, named because Hi is neutral hydrogen and H2 is ionized hydrogen. H2 regions can expand because ionized gas is hot, often around 10,000 degrees Kelvin. That heat creates pressure, and the pressure pushes outward into the cooler surrounding medium. So, an emission nebula is often not static. It is an expanding bubble or cavity carved into a larger molecular cloud. The hot stars at the center ionize and heat the gas, driving it outward. The boundary between the hot ionized region and the cooler, neutral or molecular region can become a bright front, an ionization front where radiation meets denser material. These boundaries are where many of the most striking shapes form. If the surrounding cloud is uneven, clumpy, and filamentary, as most clouds are, then the ionization front eats into the material at different speeds. Dense clumps resist longer. Less dense regions are cleared quickly. The result can be pillars, globules, ridges, and sculpted walls, like cliffs being eroded by a steady wind of light. It's tempting to imagine these structures forming quickly because they look dramatic, but the timescales are long. The wind of light has patience. Now, within these sculpted regions, something else can happen. As the ionized bubble expands, it can compress the surrounding gas. Compression can increase density. Increased density can help gravity take hold. And that means emission nebulas can both destroy and create. They can disperse gas, preventing further collapse in some areas, while also triggering star formation in others by squeezing material into denser configurations. This is one of the galaxy's quiet feedback loops. Young, massive stars form from a cloud. Then their radiation and winds reshape the cloud, sometimes halting star formation nearby, sometimes triggering new star formation at the edges. Over millions of years, the region becomes a complex mixture of cleared cavities, dense remnants, and newly forming stars. So, in a single nebula, you can have a timeline. Older, massive stars in the center, younger protostars embedded in the compressed outskirts, and dark, dense cores still waiting their turn. Now let's drift to reflection nebulas, which are softer in mood. A reflection nebula shines because it scatters light from nearby stars. The gas in these regions is typically not ionized strongly enough to glow on its own in visible emission. Instead, dust grains catch starlight and redirect it toward us. Reflection nebulas often look blue because shorter wavelengths of light scatter more efficiently, similar to why Earth's sky is blue, but the exact color depends on the illuminating star and the dust properties. If the nearby star is cooler and redder, the reflection nebula can appear different. If the dust is thick, it can also redden the light by absorbing more blue wavelengths. Reflection nebulas are, in a sense, the universe's gentle lampshades, soft light in a thin medium, revealing dust that would otherwise be invisible. They often appear near star-forming regions because those are places with both dust and bright stars. But they can also occur wherever a bright star is close enough to a dusty cloud for the cloud to be illuminated. Unlike emission nebulas, which depend on ionizing ultraviolet radiation, reflection nebulas depend more simply on geometry, light source, dust cloud, and observer alignment. They can be quiet, delicate structures, wisps, and curtains of dust that catch starlight like silk. Then there are dark nebulas. Dark nebulas are not glowing. They are visible because they block light. When you see a dark lane cutting across the Milky Way, or a dense black patch in front of a star field, you are seeing dust that absorbs and scatters background light. The nebula is there, but it announces itself by subtraction. Dark nebulas are often the densest and coldest regions, the ones most closely connected to future star formation. Deep inside them, temperatures can be extremely low, perhaps only 10 degrees above absolute zero. Molecules can survive. Dust grains can accumulate icy mantles. Gas can cool effectively, and in the densest cores, gravity can begin to win. So, in a calm way, dark nebulas are promising. They are not empty. They are full of material. They are the places where the next generation of stars may already be beginning, hidden from optical view. If emission nebulas feel like the bright, public face of star birth, dark nebulas are the private interior, the quiet room where the slow work happens. Now, as we talk about these different nebulas, it's helpful to remember that the galaxy is full of transitions. A giant molecular cloud can contain dark regions, reflection regions, and emission regions all at once. New stars form inside dense pockets. Some of those stars become massive and begin to ionize their surroundings, creating emission nebulae. Their light also reflects off dust, creating reflection nebulae. And their radiation and winds can carve cavities, leaving behind dark pillars and dense globules. Nature layers processes. Now let's move to a different kind of nebula entirely, planetary nebulas. The name planetary nebula is a historical accident. Early telescope observers saw small, round, disc-like shapes and thought they resembled planets. They are not related to planets in origin. They are related to aging stars. A planetary nebula forms when a sun-like star reaches the late stages of its life. After spending billions of years fusing hydrogen into helium in its core, a star like the Sun eventually runs out of hydrogen in the core. It leaves the main sequence and becomes a red giant. Later, it may fuse helium into carbon and oxygen in a core, surrounded by shells where hydrogen and helium fusion occur. The star expands, cools at the surface, and becomes luminous and unstable in its outer layers. Over time, it begins to lose mass. Pulsations and stellar winds push the outer envelope outward into space. The star sheds its outer layers, gently compared to a supernova, but still dramatically compared to anything in human experience. Eventually, the hot core is exposed. This core becomes a white dwarf, extremely dense and very hot. The ultraviolet radiation from the white dwarf illuminates the expanding shell of gas that used to be the star's outer layers. The gas becomes ionized and glows, forming a planetary nebula. Planetary nebulas are often beautifully symmetric rings, shells, bipolar lobes, intricate filaments. That symmetry is deceptive because the physical reasons can be complex. Interactions with companion stars, magnetic fields, rotation, and variations in mass loss can sculpt the outflow into different shapes. And planetary nebulas do not last long by cosmic standards. They expand and disperse into the interstellar medium over tens of thousands of years, sometimes a bit more. The central white dwarf gradually cools. The nebula fades, Its material merges back into the galaxy, enriched with elements the star produced during its lifetime, like carbon and nitrogen. So, a planetary nebula is not only a farewell, it is also a contribution. It returns processed material to the interstellar medium, adding to the dust and gas that will form future stars and planets. In that way, even gentle stellar death becomes part of the galaxy's long-term fertility. Now, another dramatic nebula type, supernova remnants. A supernova remnant forms from the explosive death of a massive star or from certain types of thermonuclear explosions involving white dwarfs. In the massive star case, the story is intense, but we can tell it calmly. A massive star lives fast and burns hot. It fuses heavier and heavier elements in its core, building layers like an onion: hydrogen, helium, carbon, neon, oxygen, silicon, and eventually iron. Iron fusion does not release energy, it costs energy. Once an iron core forms and grows too heavy, the star can no longer support itself. The core collapses in a fraction of a second, triggering a shock wave and an enormous explosion, a core collapse supernova. The explosion sends stellar material outward at thousands of kilometers per second. That fast-moving ejecta slams into the surrounding interstellar medium, creating a shock front. The shock heats gas to extremely high temperatures, producing X-rays and accelerating particles to near light-speed cosmic rays. Magnetic fields become tangled and amplified. The remnant glows across the electromagnetic spectrum: radio, optical, X-ray, and sometimes gamma rays. Supernova remnants can have delicate filamentary structures, expanding shells, knots of enriched material. They are chaotic, but with a kind of patterned turbulence. Over tens of thousands of years, the remnant expands, cools, and eventually merges into the interstellar medium, distributing heavy elements widely. Supernova remnants are among the universe's most important recycling events. They produce and distribute many of the elements heavier than helium. They can trigger star formation by compressing clouds. They shape the structure of the interstellar medium on large scales, creating bubbles and cavities. So even the most violent nebula type still participates in the same long, slow cycle. Stars form from clouds. Stars live and alter their surroundings. Stars die and return material. Clouds form again. Nebulas are the visible parts of that cycle. Now, there is another subtle type of nebula phenomenon that is worth resting into for a moment: diffuse interstellar nebulosity, faint clouds illuminated by the general glow of the galaxy or by nearby stars. Sometimes called cirrus in infrared images. In infrared maps, you can see wispy structures across large areas of the sky, thin dust emission resembling high-altitude clouds on Earth. These are not isolated objects, so much as the texture of the interstellar medium itself. They remind us again that the galaxy is full of material, even when it looks empty. And there is a particularly calm kind of nebula to contemplate: molecular clouds, as seen in radio and millimeter wavelengths. Molecular clouds are often invisible in optical light, but they are the main reservoirs of star-forming gas. They can be traced by molecules particles like carbon monoxide, which emits in rotational transitions detectable by radio telescopes. The presence of CO is like a signpost. Where there is CO, there is usually a lot of H2, even if H2 itself is hard to detect. Molecular clouds have internal structure, filaments, cores, clumps, cavities. They are shaped by gravity and turbulence. They are influenced by magnetic fields. They can be stirred by nearby supernova shocks and stellar winds, and within them, dense cores can collapse to form stars. So even when a nebula looks dark in visible light, it can be bright in other wavelengths. The universe is always speaking. We just need different ears to listen. This brings us to an important idea for understanding nebulas. What you see depends on how you look. Optical light shows glowing ionized gas and dust silhouettes. Infrared shows warm dust and embedded star formation. Radio shows cold gas and molecules. X-rays show extremely hot shocked plasma in supernova remnants and energetic regions. No single image shows the real nebula in full. Each is a layer of reality, a slice through the physical processes. If you want a soothing mental picture, imagine a nebula as a layered landscape. At the deepest layer, cold molecular gas is gathering and cooling, almost invisible. Above that, dust is shaping what light can pass through. Near hot stars, ultraviolet radiation creates a glowing skin of ionized gas. And in the most energetic events, shock waves heat the gas so strongly that it shines in X-rays. A nebula is not one thing. It is a region where multiple states of matter exist side by side. Now, let's talk gently about why nebulas have shapes at all. If gas and dust were perfectly uniform, a nebula would be a smooth, faint haze. But the interstellar medium is not uniform. It is turbulent. Turbulence in space is different from turbulence in air because the medium is so thin. But turbulence still creates density variations, clumps, and filaments and sheets. Gravity also creates structure. If a region becomes slightly denser, it can attract more gas, becoming denser still. This is the seed of collapse. Magnetic fields add another dimension, guiding charged particles and influencing how gas can move across field lines. Radiation from stars can carve cavities and compress boundaries, producing bright rims and shadowed pillars. And shock waves from stellar winds, expanding H2 regions or supernova explosions, can sweep up material into shells and filaments. So, the shapes of nebulas are the visible record of invisible forces. In a photograph, you might see a bright arc. That could be an ionization front. You might see a thin filament. That could be a shock-compressed ridge, or a magnetic field-aligned structure. You might see a dark pillar. That could be a dense clump resisting erosion. You might see a bubble. That could be a cavity blown by winds and radiation from young stars. Nebulas are the galaxy's handwriting, written in gas and light. Now, because this is a sleep-friendly script, it can help to move through a few famous examples, not as a list to memorize, but as gentle scenes. Imagine the Orion Nebula, a bright region visible even to the naked eye under dark skies. It is an H2 region, powered by hot young stars. Within it, there are protoplanetary disk proplyds, seen as small dark silhouettes or bright-rimmed shapes against the glowing background. Those disks are the early stages of planetary systems exposed to harsh radiation, being sculpted in real time. Or imagine the Eagle Nebula, famous for its pillars, dense columns of gas and dust. The pillars are not permanent. They are temporary structures, being slowly eroded by radiation from nearby stars, while also sheltering denser cores within that may be forming new stars. Or consider the Horsehead Nebula, a dark nebula seen in silhouette against a glowing emission region behind it. The horsehead shape is a dense clump being shaped by radiation, a visible outline of dust that blocks the background light. Or the Ring Nebula, a planetary nebula with a bright ring-like shape, an expanding shell illuminated by a hot central white dwarf. Its apparent ring is a projection effect, a three-dimensional structure seen from our viewpoint, glowing in specific emission lines. Or the Crab Nebula, a supernova remnant from a recorded explosion in 1054, containing an energetic pulsar at its center. The nebula glows with synchrotron radiation from relativistic electrons spiraling in magnetic fields, and with emission from shocked gas. Each of these is different, but each is still part of the same story: matter in motion, shaped by energy and time. Now, let's step back and ask, in a calm way, what nebulas mean for the galaxy as a whole. Nebulas are the intermediate state between stars. They are where material waits before becoming stars, and where material returns after stars change or end. They are the reservoirs of future starlight and the archives of past starlight. They also regulate star formation. If the interstellar medium collapsed into stars too efficiently, galaxies would burn through their gas quickly and become quiet. But star formation is inefficient, partly because feedback from stars, radiation, winds, supernovae stirs and heats the gas, dispersing clouds, preventing runaway collapse. Nebulas are therefore not only nurseries, they are control systems shaped by feedback loops that keep the galaxy stable over billions of years. It's a comforting thought. The galaxy balances itself. Now, let's move into one of the most soothing aspects of nebulas: their timescales. On human timescales, the night sky feels fixed. Nebulas feel like permanent objects. But on cosmic timescales, nebulas are transient. An H2 region might last a few million years before its massive stars evolve and the gas disperses. A planetary nebula might shine for tens of thousands of years before fading. A supernova remnant might remain distinct for tens of thousands of years before blending into the interstellar medium. A molecular cloud might persist for tens of millions of years, forming stars in episodes before being dispersed by internal feedback and galactic dynamics. Even the grandest structures are temporary. But temporary in the universe can still mean unimaginably long to us. Long enough to feel like eternity. Long enough to let your mind rest in the idea that change can be slow, steady, and beautiful. Now, a gentle note about how astronomers learn what nebulas are made of. They use spectroscopy. When gas emits light, it often emits at specific wavelength spectral lines associated with transitions in atoms and ions. By measuring these lines, astronomers can identify elements and ionization states. They can estimate temperatures, densities, and velocities through Doppler shifts. Molecular clouds observed in radio show molecular lines that reveal chemistry and conditions. Carbon monoxide lines trace gas distribution and motion. Other molecules trace denser regions or colder temperatures or the presence of shocks. Dust emission, observed in infrared, reveals dust temperature and mass. Dust absorption, seen as extinction and reddening, reveals how much dust lies along the line of sight. By combining these techniques, astronomers can turn a nebula from a pretty picture into a physical map, where the gas is, how hot it is, how it moves, how it's being energized, and how it's changing. But tonight, we don't need the full technical apparatus. We only need the calm result. Nebulas are not mysteries in the dark. They are understandable in detail, and the understanding makes them even more peaceful because it turns drama into process. Now, let's return gently to the role of dust, because dust is the quiet artist behind many nebula scenes. Dust absorbs starlight and re-emits it in the infrared. This means star-forming regions can be hidden in optical light but luminous in infrared. Dust also helps molecules form by providing surfaces for chemical reactions. In cold regions, dust grains accumulate icy mantles, storing molecules that can later be released into the gas phase when warmed. Dust also polarizes light, and that polarization can reveal magnetic field directions. By measuring polarized starlight passing through dust, astronomers can infer the alignment of dust grains, which tend to align with magnetic fields. This provides another window into the hidden forces shaping nebular structure. So dust is not just a nuisance that blocks our view. It is part of the physics, part of the chemistry, part of the story. Now, let's explore the quiet connection between nebulas and planets. Planets form in disks around young stars, protoplanetary disks made of gas and dust. The dust in these disks comes from the interstellar medium, processed through molecular clouds and nebular environments. The elements that make rocky planets, silicon, magnesium, iron, oxygen, were forged in earlier stars and dispersed by supernovae and stellar winds into nebulas. The carbon and nitrogen that build organic chemistry were likewise enriched through generations of stellar life and death. So, when you see a nebula, you are seeing the supply chain of worlds. It's a slow cosmic chain. Stars make elements. Elements become dust. Dust gathers in clouds. Clouds form new stars and disks. Disks form planets. And eventually, those planets orbit the new stars while the galaxy continues. Nebulas are the linking chapters. Now, because sleep-friendly narration benefits from gentle repetition, here are a few anchor ideas, revisited softly. A nebula can glow because it is energized by starlight. A nebula can shine because it reflects starlight. A nebula can appear dark because it absorbs and blocks starlight. A nebula can be a cradle where stars begin. A nebula can be a memorial where stars have ended. And a nebula can be an archive holding the material history of many generations. Now, imagine drifting through a nebula not physically but mentally. You are not moving fast. You are not a spacecraft cutting through gas. You are simply letting the concept surround you. At first, you notice the scale, light years of distance, layers upon layers of thin matter. You notice that the empty spaces are full of faint material. You notice that the bright regions are not dense walls, but luminous skins of ionized gas. You notice dark lanes, dust that marks where the density is higher. Then you notice the source of light, stars, often young and hot. Their ultraviolet radiation shapes the gas, and their winds sculpt cavities. In some places, you sense shock front regions, where expanding gas meets quiet gas, compressing it, heating it, forming bright rims. In other places, you sense the cold interior. Molecular gas cooled down enough to host chemistry, with dust grains carrying ices. There, gravity is quietly preparing the next generation. And in still other places, you sense the aftermath of violence. Supernova shock waves moving outward, leaving behind turbulent filaments and a hot interior, distributing heavy elements into space. This is what nebulas really are, the interaction zones of a galaxy. Now, it can also help to correct a common mental image. Nebulas are often shown in photographs with extreme contrast and color saturation, revealing intricate structure. The human eye, if it were there, would not see the same brightness and color. Many nebulas are too faint for our eyes to see color well, because color vision requires brighter light. Under dark skies, you might see a nebula as a pale gray glow, perhaps with hints of greenish or reddish in the brightest regions, but much subtler than in photographs. That doesn't make the photos fake. It just means the photos are translating a faint universe into a visible one for us, gathering light for minutes or hours, using sensitive detectors, and sometimes combining narrowband filters. In a calming way, this is reassuring. The universe is not shouting, it is whispering, and our instruments listen carefully. Now, let's give attention to one more kind of nebula-related structure: bubbles and superbubbles. When many massive stars form in a cluster, their combined winds and radiation can blow large cavities in the interstellar medium. Later, when some of those stars explode as supernovae, the combined energy can carve even larger bubbles. These cavities can be tens or hundreds of light years across. Their edges can be swept up shells of gas and dust, sometimes triggering star formation along the rim. The interior can be hot and tenuous, filled with shocked gas. A superbubble is like a long-term collective footprint of stellar activity. It shows how groups of stars reshape the galaxy on large scales. And it shows again that nebulas are not isolated decorations. They are connected to the broader ecology of the Milky Way. Now, if your mind likes gentle numbers, here are a few that can provide quiet perspective. Typical densities in emission nebulae might be a few hundred to a few thousand particles per cubic centimeter, still extraordinarily thin. Molecular cloud densities can be higher in dense cores, tens of thousands to millions of particles per cubic centimeter, yet still far thinner than any earthly atmosphere. Temperatures vary widely. Cold molecular regions around 10 Kelvin, warm ionized regions around 10,000 Kelvin, supernova remnant interiors, millions of Kelvin. Sizes range from small planetary nebulas a light year or less across, to giant H2 regions, tens or hundreds of light years across, to molecular cloud complexes spanning hundreds of light years. Timescales range from thousands of years for some planetary nebula evolution and young supernova remnants, to millions of years for H2 region development, to tens of millions of years for molecular cloud lifetimes. All of this is slow enough to feel stable and dynamic enough to be alive. Now, let's gently connect nebulas back to the simple idea of starlight. A star is a stable source of energy created by nuclear fusion, but the star does not exist alone. Its radiation flows outward and meets the interstellar medium. This, where that radiation meets gas and dust, nebulas appear. So, nebulas are, in a way, the visible conversation between stars and space. Some parts of the conversation are loud: ionization fronts, shock waves, supernova remnants. Some parts are quiet: reflection, faint dust emission, molecular chemistry. But it is all the same dialogue: energy and matter interacting. Now, one last soothing pass through the cycle as a continuous, unbroken story. Gas and dust drift through the galaxy as the interstellar medium. Over time, gravity and galactic motion gather material into molecular clouds. Inside these clouds, dense cores form. Some collapse into new stars. If massive stars are born, their radiation and winds ionize surrounding gas, creating glowing emission nebulas and expanding H2 regions. These regions carve cavities and sculpt pillars and bright rims. They can trigger new star formation at their edges while dispersing other regions. Meanwhile, lower mass stars live long lives. When they age, they shed their outer layers, forming planetary nebulas that glow briefly before fading. Massive stars, after short, intense lives, explode as supernovae, leaving supernova remnants that expand and mix heavy elements into the interstellar medium. Those enriched materials become part of future clouds. Dust forms and grows. Molecules assemble on dust grains. New stars form again. And through all of it, nebulas appear wherever the conditions make them visible by emission, reflection, absorption, or shock. The galaxy keeps moving, but it does not rush. Nebulas form, glow, fade, and merge back into the background, while the long cycle continues. Now, let your mind rest on a final image, calm and simple. Picture a dark lane across a star field, a dust cloud, dense enough to block light. In the depths of that darkness, cold gas is gathering. Nearby, a young cluster of hot stars illuminates the edge of the cloud. The boundary glows softly. The ionized gas forms a bright rim. Behind it, dust reflects blue-white starlight in a faint haze. In the distance, a bubble expands slowly, its shell traced by thin filaments. Somewhere else, far away, a planetary nebula drifts outward like a quiet ring, shining briefly as its central white dwarf cools. And somewhere else, a supernova remnant spreads filaments through space, mixing the elements of a former star into the next generation's raw material. All of these are nebulas, clouds of gas and dust, visible because of light and time. Not hurried, not permanent, just part of the galaxy's gentle breathing. Let that thought settle. A nebula is a place where the universe shows its process. And the process is steady enough to be soothing. Matter cycling, energy flowing, structure forming and dissolving over timescales so large that they make human worry feel small. In the quiet of this moment, you can let the nebulas do what they always do: drift, glow, fade, and become, once again, the invisible material of future starlight. Sweet dreams.